You know, back in early '96, where heat really started to develop in data centers, different products of fan doors, a ducted system, the first generation heat containment, moving on to second generation heat containment, and then finally to aisle containment. First off, I thought it'd be good to get on the same page. And a lot of times what we talk about in a data center and why we want to use a containment strategy is we see a lot of chaos air distribution. And simply chaos in the data center represents itself as a large mass of air being moved into the data center with the expectation that it's going to create turbulence and be able to get the cool air in front of the IT equipment. Consequently, on the backside, there's a large expectation that that same turbulence is going to move the warm air back to the air conditioning system. Well, we consider that chaos. And really, how does it manifest itself in a data center? Well, like I said, the legacy design systems where we're actually providing an oversupply of air to be able to get this chaos system to work. And make no mistake, your data center was designed with a chaos air distribution strategy in mind and probably working effectively. However, our point is you can do one of two things. You can make it work more efficiently or have the same system carry more load. And how do we do that? Well, the cool air in your data center is used for multiple different purposes. Ideally, it's meant to cool your IT equipment, its primary goal, but it's also used to create a cool air envelope that is meant to move warm air away from your IT inlets, those hot spots. You actually use an oversupply of cool air to keep the hot spots at bay. And then obviously I've seen a lot of different data centers that use an oversupply system to help move that warm air back to the return system. Actually try to create a velocity of movement in hot aisles or at the end of rows to get that hot air back. And then again, to create this bubble or envelope in front of your IT equipment. That also creates a lot of opportunity to recapture that waste. One of the other things about your data center, it's nice to talk about your data center in a static state, but the fact is it's not. It's highly dynamic, meaning multiple changes in any part of the system can create changes in your cooling performance. Consequently, it's a very dynamic state. So everybody needs to understand that their data center, what they do today, as I go to a floor tile and I pull up a tile, that could potentially have impact on how your data center performs somewhere else in the data center. Not necessarily in that general area either. It could be anywhere else in the data center. So a lot of the things that we like to talk about help drive predictability and remove that unpredictability. First, I thought it'd be good to talk about how does it actually manifest itself in the data center? What are those bad behaviors that are actually happening? Now, we see it as recirculation, air stratification, and bypass air. Simply, the recirculation of air is air from a piece of IT equipment that's already been exhausted, somehow makes it back to the inlet of another piece of IT equipment. Maybe the same one, maybe a different one, but obviously recirculates that air. And as you have a temperature rise through your IT equipment, getting exhaust air back into the inlet obviously can be bad because it just multiplies on itself. Air stratification. Air stratification in a data center, part of that chaos scheme that I talked about, is actually part of a design criteria for the data center. And in fact, stratification is normally meant to slowly keep all the warm air at the high levels, the high elevations in the data center, then have your AC system pull from that high level. Ideally, that heat is at the high level in a room like this. You really wouldn't have a problem with the top 3 feet of this room being warm because you don't have any IT equipment up there. However, what happens when that heat mass extends down into the U space? That creates a problem. And then of course bypass air. Air that I spent all this money to cool, and I've spent all this money to blow it into the data center, and it doesn't cool any IT equipment. It just goes right back to the AC system. Obviously problematic. Here's a good picture in a real-time CFD to look at what's happening with recirculation and how that happens. As you can see, the hot air is just circulating around from the back of this piece of equipment and going back into the inlets, obviously raising its overall temperature. So you can see the bottom is quite cool. So the ideal place for a piece of IT equipment in this type of data center would be in the bottom U space. And you've effectively eliminated the capability to use the whole top half of this rack. Obviously, we try to see that we can maintain some type of manufacturer inlet temperatures around 95, but as you recirculate, keep in mind if you add 10 degrees every time you put the air through your IT equipment, you're very quickly at 95 or above it. Temperature stratification. Remember that heat deck that I talked about? Well, this is an example of that heat deck coming down into the usable use space of the actual rack and causing an exceeding of the inlet temperatures. This is very typical in a data center. We see this a lot, particularly in low deck data centers, where you've only got a couple of feet and you're pushing the design limits of the data center or exceeding the design limits. One of the little known things about stratification, and I don't know if anybody likes oil and vinegar on their salad, but when you look at the oil and vinegar bottle, you get nice layering until you cause some type of disturbance and you shake it up. Your stratification system kind of relies on the same thing, is that it wants a quiescent environment so it can actually maintain a nice layer high in a data center so your air conditioning system can pull that hot air down. Problem is the data center is highly dynamic. Too many other disturbances create turbulence in that environment, and it's not unusual to get the hot air causing almost a waterfall effect. How does that happen? Well, that bypass airstream could actually be causing that. That bypass airstream is cool air that is coming out in a jet stream fashion from a perf tile, hitting the ceiling, creating what is essentially a mushroom cloud of cool air, half of it moving warm air away, the other half of it going back to the AC equipment. But when it does that, it disturbs that layering effect that is really required for stratification to work well. When that happens, that not only creates an efficiency problem for your crack unit that is really now just seeing its own return being fed with its own supply, but the other air that is splaying off the other direction is moving heat away from the AC unit. So you're kind of getting a double hit there, and this is a pretty significant problem. Well, containment can obviously help with all of these things, and I'm sure you've heard about a variety of different containment strategies. And the way we like to look at it is there's really three types of containment that you can deploy. I'm sure you've heard a lot about cold aisle containment, hot aisle containment, or rack-based chimney containment. And normally, you can deploy that in a couple of different phases. You can do it partially, or you can do it total containment. And then when you actually implement it, a lot of times, a lot of these containment strategies bolt to the rack. Some of them are independent to the rack. So really need to make decisions around all these different containment strategies and what are the trade-offs and benefits of some of those containment strategies. We'll talk a little bit about that in a minute. But a lot of times, what's difficult to understand is your site physically in the data center will constrain some of these decisions. Meaning it may be very well, if you have multiple data centers, you may have a data center that's quite well suited for a chimney-based heat containment, but not at all suited in another data center in your same portfolio, and you may need to deploy cold aisle containment. So there's no one religious type decision that will drive you to one type of containment strategy or another. And in fact, a lot of our customers will mix and match different containment strategies depending on what they're deploying. For instance, recent customers looking at deploying a new high-density pod in an existing legacy data center, set up in a legacy 75 watts a square feet. Not much, right? That's not much power for high density. And in fact, they'd have to clear out a significant amount of space to handle that. Well, they decided to put an independent system in to be able to handle that heat and power. Heat containment is a good way to be able to contain that heat, to make sure that heat from that new load didn't affect the rest of the data center. And cold aisle containment in the same location, we're actually combined together to make sure that the rest of the heat from the data center didn't affect the new load. So a different way to look at it, but was able to solve the problem with a containment strategy.